Hey chemists, how you going? Just want to talk you through this reaction rates inquiry task. So essentially what you're going to be doing is running a simulation from PhET, or I don't know how to pronounce it, but it's an awesome website, really good simulations to do with physics, chemistry, lots of cool stuff there. So basically you need to get the simulation by going to the website, following the instructions there to get the rate of reaction simulation. So basically the first, I guess we'll go through the learning goals. We're going to look at how temperature, concentration and activation energy change the rate of reaction. Now, you've already looked at that theory before, you've watched videos, read textbook information, but this simulation might give you a different perspective and maybe kind of clarify a few things that you may not have realised by looking at that information beforehand. So first thing, we're going to look at the single collision simulation and we're going to complete the table. So basically, changing a variable, what are the observations, and explain this change using collision theory. So I'll show you what the simulation looks like. So we've got some different tabs: single, many collisions and rate experiments. So first we're going to look at single collisions. So basically down the bottom here, you've got an example of the reaction. So you've got particle A, which is the yellow one, plus B and C together, reacts to form A and B together and C by itself. So basically you've got the breaking of this bond and the formation of a new bond here. Now that's a reversible reaction, so the reactants make products, the products make reactants. It goes back and forward. So basically we've got a bit of a molecular launcher here, and you can kind of see that it's like a pinball machine. So basically that's kind of showing how much energy this particle is. So the less energy you give, it's kind of like saying there's less kinetic energy and then there's more kinetic energy. Realistically, the kinetic energy would be brought about by potentially the amount of heat that you're transferring in this reaction. Maybe you have to heat it up, or maybe it's got to do with stirring, providing some kinetic energy by stirring a solution. So that's kind of what it's simulating. So let's just kind of go max, we'll go halfway here. So you can kind of see the particles are kind of pinballing each other. So at the moment here, is there a reaction happening? No, there's not. I guess the particles are colliding, but we don't actually see the formation of product there. So that is an observation that we might have. So if we go back to our variables, what did we change? Well, we can kind of, and I can reset at any time here, I believe. Yes. So if the variable I'm changing is the kinetic energy, or the speed, or the power that we're putting in the pinball, it doesn't matter how you explain it. We don't have a reaction happening here. But now, if I give it more power, we can see that there is actually something happening here. So when the collisions are occurring with enough energy, we've got the formation of products happening. So reaction, reaction, because every time it changes, and then all of a sudden, we've got something, the angle changing ever so slightly, and then there's no longer a reaction. It's going to keep bouncing around a little bit. So this is kind of showing me that particle orientation matters. It's not just the amount of energy. The particles also have to collide in the correct orientation to form products. So there's some other things we can change as well. And by changing those variables, I want you to say what effect that has on the reaction occurring. So you can raise temperature, lower temperature, so you could kind of set it going and then raise the temperature by heating, and then you have to kind of hold that down, and you can see up the top, I'm just pointing at the screen, you guys can't see that, it's affecting the kinetic energy, and then in turn how's that affecting the reaction. Another thing is you can change the angle, so you can do a bit of an angled shot. And how does that affect the reaction? So how does that affect how quickly the reaction forms products? There's no stopwatch on here at the moment, but you can have a look at some different bits and pieces that kind of show what's happening in different ways. So let's go back here. Basically, just completing the table, nice and easy. So the second task is, now that you've learned how temperature, concentration and activation energy will change the rate of reaction, we want to try and complete this table here. Now this is using the rate experiment simulator to test. We want to keep other variables constant. So in this table, write down a prediction, what's going to happen. When we increase temperature, how's that going to affect the rate of chemical reaction? Test using the simulator, record observations in this box here, and then explain your observations using particle theory, rate of reaction theory, and there's a few kind of guiding questions there. Now, please feel free to put as much detail in here as possible. You don't have to keep to that small little box. Extend it, go nuts, basically. Okay. So, what are the variables we're changing? Temperature and concentration of reactants. So, that tells me when I go here and go to rate experiments. Hold on. Sorry, my face is in the way here. Get rid of that. So, if I reset. Okay, what's going on here? So it's the same reaction, A plus B and C goes to the opposite, but this time you're kind of pumping things in, okay? So you can do that and do a certain number of pumps and play around with it a little bit, but I think in order to keep the variables constant, what we should do is use this stuff up here. So if I'm changing temperature, increasing and decreasing, I want to keep my particles the same, the concentration of particles the same at the beginning. So you could do, say, I don't know, 10 of A and 10 of B and C, right? Now you can do whatever you want, but just whatever you do, obviously keep it consistent when you're changing that temperature variable. So if I do that, there's a stopwatch down here as well. You guys can't see that, I don't think. Where's the stopwatch? Show stopwatch, cool. So that's there. So I could keep that there, and I could go begin experiment and start my stopwatch. And there's stuff going on here. Now, I have just moved something. How did I get rid of that? Oh, sorry. Okay. So if I have a bar graph there, you can see how much product we're forming. So after 400 seconds, it's in seconds, you can see that the change over time. So we've got 8 of each reactant particle and 2 product particles there. And you could keep it going for, say, I don't know, 1,000 seconds or something like that. And then we stop the experiment and we see, okay, after 1,000 seconds, just an arbitrary number, do whatever you want. This is the change that we've got. So we've got 3 product particles. So now if I reset and I go back to 10 and 10 and I increase the temperature, let's just absolutely crank it. Okay. And then I'll show the stopwatch. I'll have my bar graph again. You can change the type of graph, obviously. And then we'll start. And then we'll start our stopwatch. And we'll go for the same amount of time, and we'll see how that increase of temperature affects the rate of reaction. And what's happening here? Now, you can see that the products are being formed pretty quickly, but there's also a reverse reaction happening too. So realistically, that 1,000 second mark might be a little bit too much because it's really kind of going back and forth really quickly. So I could maybe say that the product particles were formed very quickly, and then there's a change back to forming reactant particles because it is a reversible reaction. So if I end the experiment right there, that endpoint probably isn't indicative of what really happened. So maybe I need to go back and change my timing, or just explain what happened a little bit, because it happened obviously a lot quicker. So then I could reset, change the concentration of chemicals. Maybe I'll figure out my times. I might go for 100 seconds instead. And now this time I'm going to increase my concentration of reactant particles, and I'll have the temperature set at this level, maybe in line with this. I'll begin my experiment and I'll start my stopwatch, have my bar graph. And then it's got a mouse here as well. So maybe, I was saying 100 seconds, that's not 100 seconds obviously, it's a bit late. So it looks like this, what timing is this? I can't figure this out. This is slow. Is that the seconds? No, That's way slow. So this timing is really throwing me. I have no idea what measurement it is. Alright, anyway, let's stop at 1,000 again. I guess we'll kind of try and just observe what's happening here. So does an increase in concentration of reactant particles change something compared to a decrease? So if I start again, I go back to 5 and 5, and I start my experiment. Stopwatch there, and show my bar graph. Is there a difference maybe in the proportion of reactants that have turned to products? So not the whole number, but maybe something like a percentage. Like if there's less particles, is there going to be a greater percentage of product or a lower percentage of product in that 1,000 seconds? And you can probably kind of see that when there's less reactant particles, they collide less frequently because there's less of them, and there's also a lower chance that they're going to orientate correctly because of that reduced number of particle collisions. So we'll stop there, stop the experiment, and we'll see that not a single one actually produced product. So that kind of gives us an indication. So look, if you're someone that has read the theory, really understood it, the ins and outs, this task will be pretty straightforward to you. If you're someone that has found it a little bit difficult, maybe this simulation will help you to visualize what's actually happening with these particle collisions, with changing these variables. Something that I didn't actually go through is the activation energy. So how that activation energy, when you're increasing temperature or decreasing temperature, how that affects those reactants turning into products. Thanks guys, hopefully this helped. Good luck with your task today.